Hello, everyone. Welcome back to the AAS YouTube channel, and this is part of the good stuff. This is the AAS Journal Author Series, and I'm super happy to have Yuki Kaneko with us today. Hey, Yuki.
Hi, Frank. How are you?
It is August 26th, 2021, and I'm doing very well in Phoenix, Arizona. And where are you located, Yuki?
I am in Istanbul, Turkey.
Istanbul.
Yeah.
You
Yes.
have the honor of being the first person I've ever done from Turkey.
So I am very honored. I'm very humbled. Thank you.
So are
Thank
you like Istanbul? Are you in Istanbul?
So we are kind of at the edge of Istanbul. We're actually technically it's Istanbul, but I am away from city center.
Okay.
But yes, I am in Istanbul, like Asian side of it.
Okay.
Yeah.
Okay. Very cool. Very nice. I hear a lot of things in the news about various parts of Europe or in a big heat wave. Or how's the summer there where you're going? Is it super hot or is it sort of normal or?
Right now it's okay, but before, like in July, I think it was really hot and a lot of wildfires, forest fires. Southern part of Turkey. There are so many of them, and that was kind of really devastating fires. But now everything is under control, and yeah, now it's much more controllable.
Cool. Cool.
Yes, weather-wise, the temperature-wise also.
Very good. Yeah. Very good. So you're obviously in your home office there. So very nice.
Yes.
Let's say one other thing. Did you do holidays? Did you do summer holidays this year?
Yes, we just came back actually last week. I was in. We have a summer house in the Asian side of, right by the sea.
Oh, very nice.
We just went there. Yeah.
Very nice. You got in the water a little bit and played around.
Yeah, but it was pretty windy there, so wavy. The sea was really wavy, so I didn't enjoy that much, but still it was relaxing.
Surfs up.
Yeah.
Very cool. Yuki, what do you like to do for research?
Actually, I do gamma ray spectroscopy. I started with gamma ray bursts, GRBs. All my PhD, I did all GRB research with gamma ray spectroscopy, nice. Prompt emission. And then after I moved to Turkey, I started looking into more SGR, the soft gamma repeater bursts. So it's a different type of burst and different type of spectra, but it's still gamma ray spectroscopy that I do.
That it is. Very nice. Very nice. And that is going to bring us to this very lovely APJ letter. Fermi GBM observations of the soft gamma ray repeater, SGR, J1935 plus 2154 burst for us. And Yuki, take us away.
Yes. All right. Thank you. Thank you very much. So in this paper, we're talking about spectral properties of this burst forest that we observed from SGR 1935 plus 2154. And we observed this with the Fermi gamma ray burst monitor, GBM. And right here, you can see our team members. These are our co-authors. And this SGR is interesting because this was discovered 5-6 years ago, I guess. Okay. And then we have a lot of magnetar candidates, but there are only a handful of magnetars that was observed with radio that is observed to emit radio emission. So this is one of them, and this was actually the pulsation was observed with the radio early on, and then this has been going active, burst, inactive, for like on and off for the last few years. And last year in 2020, it became active again in April, in April and May. And then, so we looked at the GBM data of this burst, and we can see that, it emitted a lot of bursts, but at the kind of close to the onset of this burst active episode, we noticed that there's like a very kind of strange looking, a lot of bursts. And this was actually reported by Swift Bat team, Burst Alert Telescope.
Okay.
So we looked at the same time period, the light curve of this event. And then we saw that in GBM, we see this, very dense burst episode, which we call here the burst forest. It was the hundreds of events in 130 seconds that we're talking about here that we call that forest.
Okay.
And so this is not just a, a series of dense bursts, short bursts that we see usually from SGRs, but some of the profile, the light curve, showed like broad peaks. These short bursts from SGRs are usually very, very short, like sub-seconds.
Yeah.
It's just like a spikes. But this one, included, and I have a light curve actually. Maybe you can show the figure 1.
Let's take a look at figure 1. There we go. Let's blow that up a little bit, and there.
Yes.
We go. Let's try there.
So that is the 130 seconds that we're talking about. And before and after this, there's so many bursts also. And our team actually reported the time integrated analysis of all these bursts. There was 150, I will say, ish bursts that we reported with Lin et al. In 2020. And this segment was excluded because this looked a little bit different for us. And this paper is the one that we're reporting, this analysis of this excluded part of the first active episode in April 2020.
Okay.
And as you can see, like at 380 seconds, for example, you see the kind of broad peak. Right, that is really a few seconds wide, which we don't see a lot from SGR. Usually in short bursts are really short.
Yeah.
But this has been observed in other events also, like 1900 plus 14 SGR. It's another SGR, or a few more SGRs, few other SGRs. We have observed something similar, but this is very rare and very strange looking. So we decided to look into this. And then we found some sort of periodicity in terms of spectral parameter evolution.
Okay.
So not that we didn't do the timing analysis, but when we look at the spectral parameter evolution, especially in this segment too, you see those segment too, it has kind of triple broad peaks.
Yeah.
Right there, right there.
Right.
So that in the light curve, we didn't see very clear pulsation or some sort of periodicity based on the period of this source.
Okay.
The period of this source is 3.24 seconds. And it's not exactly at 3.24 seconds that this peak appears. So I looked into the spectral parameters, and then actual spectral parameter, it seems to be, or the spectral component that we're talking about, that seem to appear at 3.24 seconds. So I will show you what I mean a little bit later. But so that's why we decided to look into this. And this, yes, so one more thing about this source, 1935, is that, so this is April 27th, this happens on April 27th, 2020. And then about 6 hours later, there was a NICER observation. NICER is the X-ray observatory that's on the International Space Station. And that looks at, that observes in a little bit lower energy than Fermi GBM in X-ray. And they also observed burst forest also. They didn't have anything like broad peak like that, but it's a little bit more like a segment 1 here. And then 13 hours later, I think, after that nicer observation, there was a fast radio burst.
Ooh.
And there was a X-ray burst coinciding with the FRB. So that is interesting, right?
It is.
And that was actually the first galactic FRB observed, and it's localized to this source. So that is really special, right?
It's very special.
Yes. So yeah, this source is quite interesting.
Very nice.
So in that sense also. Yeah, so then what we did was, we wanted to be very careful in terms of, background modeling, for example, right? Like, what is the burst? And like, you see like tiny bit of burst, like at 360 or 55 seconds.
Yeah.
You see like those little spikes, right?
Yeah. Right
So,
there.
by relatively speaking, that is a really, a small burst, but that is a burst, compared with the background.
Yeah, these monsters, yeah.
Yes.
Yep.
So we needed to really be careful in terms of background modeling, not to miss any burst, and also not to, overestimate, the number of bursts here. And then, so we did a very careful background time interval selected, and that's how what I was showing here in this figure, the shaded area. The shaded time intervals are the background time intervals.
Okay.
And anything else, like white part, those are the burst time period.
Yep. Okay, good.
And I needed to divide this into segment 1 and 2, as you can see here with the dashed line in blue, because this is 130 seconds, and the Fermi satellite is moving, and 130 seconds is a big chunk of time that detector to source angle changes a lot.
Yes.
And because of that, some of the detectors may be blocked the first, 30 seconds, but then it appears or something like that. So we needed to, take those into account. So we looked at all the, the time series of detector angle and source angle. And then we decided to look at, divide the source into these two for analysis purpose. But there's nothing, special in terms of, physical origin or anything like that.
Okay, very good. I'm with you.
Right. Okay. And yeah, thank you for listening.
Fascinating.
Very good. Very good. And then we decided to use 4 different spectral models to fit these time resolved spectra within this time period.
Okay.
And there we used 4 different models that's usually used for SGR analysis, and to describe that we know that describes well SGR burst spectrum. And those are the cutoff parallel, which we call COMPT, and black body, single black body, double black bodies, and black body plus parallel. There you go. Yes, and here in the table 1, I'm just presenting the COMPT model and also black body, either single black body or double black body. Right. But black body plus parallel, it turns out the statistics was the lowest significance in the sense that, so we didn't go further with the black body plus parallel, but we just looked into the COMPT and black body spectral evolution. And then
what is C-stat?
C-stat is a log. It's actually a negative of log likelihood. So it's we try to maximize the likelihood, but it's negative of log. So it's we try to minimize C-stat. Got it. And that's a statistic that we use for Fermi GBM analysis because of the number of counts per detector.
Thank you.
So yeah, we use that, and then good that you asked, because CSTAT is not like a chi-square that we cannot really, we cannot really determine. It doesn't tell you anything about the goodness of fit. It's just the maximum likelihood. So then, okay, I have 4 different models fit in all these burst spectra, and how do you determine which one describes the best? You can't really directly compare them. So we actually used what's called a Bayesian information criteria, and we calculated that takes into account the CSTAT and the number of parameters and data points.
Okay.
So that has been used to compare CSTAT or maximum likelihood statistics, and that actually is in section 3.1. You go to page 5, maybe.
Sure. There we go.
Yes.
There we go. There's your BIC.
So,
that's what I was.
Yeah. So we use the difference between BIC of all different models for each one of the spectra, and then we decided, which one is kind of best describing in terms of statistics, best describing the spectra. And
yeah, that helps. That's clear.
Yes, and I'm kind of jumping into the pages, but if you look into, if you go down one more page,
sure,
there's a figure 5 with again the yellow band.
Yep, there's our bursts.
Yes, so here's the second. It's just the example, the second segment.
Yeah, segment 2.
Yes, this one. And here you can see this yellow shaded part is best fitted or better fitted with the BB plus BB. Do you see this red, blue point?
Yes.
So this is based on BIC, the delta BIC, the difference in BIC. These are, the spectra or the time interval where 2 black bodies fit much better than single black body.
Okay. So
this is just purely based on the delta BIC, and then this is just arbitrary scale. The photon flux is just showing photon flux in y-axis, and just BB, the black point and blue points are just arbitrarily placed.
Yes.
But this tells you that the first peak, for example, around 408 seconds. Yes, that one. Within that peak, we see that there's a high energy component, definitely. So the spectra are described better with 2 black bodies.
Okay. Okay.
And then there's a transition after the yellow band. There's a transition to single black body, which we call trough. That's the part that we call trough. And then again, there's a peak spectra again, which is the middle yellow band. And then there's trough and peak and trough. So that's how we define peaks and troughs when we talk about peak and trough in this paper.
Something's turning on.
Yes, and this is purely based on the spectral analysis, right? It's not based on the light curve, it's a spectral analysis. And it turns out, you see this yellow band appears almost at 3.24 seconds. And that, I thought was really interesting when I was, looking into this. And then, I started looking into the phases, spin phases. We don't have any timing analysis here, but as I said earlier, 6 hours later, there was a nicer observation, right? And one of our collaborators we wrote a paper about that observation also, that first observation, Yunus et al. And there we were able to look at the spectral phases from the persistent emission.
Nice.
And then we assumed, okay, it's 6 hours later, right? So we assumed that, those spin phases are probably similar or same 6 hours before that event. So we kind of extrapolated that phases and then try to match here.
Yeah.
So that's what we did.
Okay.
And if you go back to figure 3.
Sure. Give me one sec. Figure 3. There we go. Nope, too much. Right there.
Yes.
Okay. Berry center.
So this is black body, 2 black body and or single black body fit. So what this is showing, so to the left is the first part of the segment 1 light curve.
Okay.
And here I'm showing the light curve as a rate. And then in right axis, there's a black body temperature. And black points at the bottom is either single black body parameter or the lower black body parameter, lower temperature black body parameter. Okay.
But just one black body.
Either one single black body, or if the spectrum was fit better with 2 black bodies,
Okay.
it's the lower black body temperature.
Got it.
Because I have a high black body and a low black body, right?
Got it. Okay.
And the blue ones are the high energy black body.
Yep, I'm with you.
So in other words, if you see the blue point, that means that spectra was fitted with 2 black bodies.
Yep.
Yeah. Okay. So this is the spectral parameter evolution for KT high and KT low. And on top, you see the nicer pulse profile.
Yeah.
And this is, again, it's extrapolated from 6 hours later, the observation 6 hours later. And this, phase cycle is just, it's just counted from Fermi GBM trigger. So it doesn't mean that much. But you can see the phases, going in at 3.24 seconds.
Yeah, nice.
And for this 2 plots, these are showing segment 1 peak. And the one on the right is the segment 1, the broad peak that I pointed out at the very beginning, 380 seconds or so. So here we don't see that much of correlation between the phase and spectral parameter.
Yeah.
We didn't see that much of strong evidence in a sense. The only thing is that maybe that this broad peak is happening at the minimum of the phase, but with one example, you can't really tell.
Yeah, fair enough.
So that was the second segment 1. But then if you go down to the figure 4, there is segment 2, the triple peak.
Yep.
And there you can see that the kind of correlation between spectral peak, the high energy component peaks at the minimum of the phases. So this,
yes, okay.
yes, so peak is not exactly correlated, but this is much stronger in a sense, like 3 in row, and it's kind of anti-correlated with the phase peaks.
Right.
So this we wanted to interpret this part, especially theoretically, and we try to kind of match this kind of pulsation or periodic behavior to the segment 1, but we did not see anything that strong in the segment 1. Only in this 3 peaks part, this was really had a strong indication. If you actually go back again to figure 2.
Yes. There.
That is the Comptonized model, the COMPT model. So this is one component model, and you can actually see the peak of the spectra, like spectral shape, how it peaks in the middle panel. Yes, the E peak. So here you can see a little better, clearer, that peak of the spectra kind of anti-correlates with the phase cycle. You see that?
Yes. Okay.
Okay. So yeah, this, is actually very nice if you're looking for, some sort of spectral, evolution behavior. And so we got really excited. And then the quantized EP index at the very bottom, it actually remains more or less the same. But also this is positive, maybe 0.5-ish, it's a constant that value. And that means it's a very hard hard, the hard meaning less soft in
more high energy,
lower energy. Yes. So that is actually, very representing a thermal spectra instead of, it's not non-thermal spectra, it's a thermal spectra.
Yeah.
So yeah, so that was the behavior that we saw. And then if you go to figure 7.
Sure.
So again, I'm still looking into segment 1 and 2 all together.
Okay, that sounds like a deal.
So this is black body, right? Okay, so if it's a thermal emission, we can estimate the emitting region. And so that's what we did. And yes, figure 7 right here. This is segment 1 and segment 2 separated, but scales are exactly the same. So y-axis and x-axis scale is the same. And this is the emitting region versus flux. And this KT equals 7 and KT equals 14 keV lines. These are not best fit lines. These are just representing kind of isothermal contour that I'm showing, assuming Stefan Boltzmann sigma t to the 4th. So, but if you look at it, 7 and 14 keV seems like all the spectra are following more or less 7 keV ish, 14 keV ish, right? So the lower black body, or single black body,
yes,
peaks. The temperature is around 7 keV, staying around 7 keV. And then likewise, the higher temperature is staying around 14 keV.
Yep.
So that's, yes. And then as you can see, the higher energy black body, the emitting regions are 1 or 2 order magnitude smaller.
Smaller, yeah.
Than lower one. And in below that, figure, what would that be? Figure 8.
Figure 8 looks like a much.
Yes. So that one, maybe you might want to make it bigger.
Oh yeah.
Because this has a lot of information. Yes.
You see the bigger version?
This now, yes. Very good. Thank you. So this combines segment 1 and segment 2.
Okay.
And because of that, I put square for segment 1 peaks and diamond for segment 2 peaks.
Okay.
Kind of very faint, but I wanted to make it not so crowded.
Right. Yeah, it's busy.
But you can see that the segment 1 peaks parameters are a little more spread out than segment 2 peaks. See that? And
yes, yes, I see what you're saying. Yes.
Yes. Kind of. It's a little bit hard to see, but this.
It's there. It's huge, but it's there.
Yes. And then you can see that again, the low KT is in red and high KT is in blue. And these gray ones are the one that's fitted by single black body.
Yes.
Yeah, so these are mostly trough spectrum, because those are the one, the non-peak spectrum. Okay. And these dashed gray dashed like a broken parallel. That is actually taken from Lin et al. That when we presented burst time integrated analysis of 150 bursts before and after this event. So it's the same active episode, but those are all short bursts. And when you actually, did you get it?
Yeah, I'm processing. I'm with you. Go ahead.
Good.
I'm with you.
Good. So you have 150 bursts before and after, or spanning that time period before and after this episode. And when we do the same thing with R square and KT,
yes,
these are kind of trends that we found.
Okay.
For high energy and low energy. It was kind of broken parallel. Here, I don't see any broken parallel type of behavior because the number of data points is probably very small to make something like that. But still, this was the just for comparison purposes, I showed that. And these blue shaded area, I have two bands, right?
Yes.
The lower one is the average plus minus 1 sigma of the bursts lower energy KT.
Okay.
And then the wider one in upper energy about 10 keV, that is one for the 1 sigma range average for the high KT of the burst, short bursts.
Okay, I'm with you. Yep.
All right, very good. So if you compare with that averages, you can see that the KTs are a little bit higher for this event. Right?
Yep.
So that's one thing. And again, see, this is R square and KT. So assuming Stefan Boltzmann, sigma T to the fourth, if you look at the radiative power, you can actually estimate or put the, yes, isoluminosity lines. Yes, thank you very much. So that is, you see the 10 to the 39 to 10 to the 41. That is a typical short burst luminosity that we see from SGRs. Short burst.
Right, and this would be the isotropic luminosity. Right. It's
yes,
not
isoluminosity.
We're not talking about jets, anything like that.
Right. Yes, exactly. So whatever the emitting radius, it's like a sphere.
I'm with you.
Yeah.
Yep. Okay.
And then the top one, kind of dash dotted line. Yes, that one is in the caption. I show the number, exact number, 2.6 to the 41. And that I actually put it by eye, where would that be like kind of maximum, luminosity for this, all these events.
The outer.
And that,
yep.
Yeah, so that is still like, a few times 10 to the 41. So that is, like upper limit of short burst luminosity, that we usually observe. So this is, this could be sort of like a, collection of short events, although some of them, the light curve, you see that it's much broader, and then there's a lot of evolution within those broad peaks.
Yep.
Okay. So that is what this is showing. And so we thought, okay, so the hot temperature, the hot black body part, that emitting region is smaller, right?
Yes.
10, maybe less than 100, but the factor of that much than the lower energy part. Right. So then we thought you have a neutron star, and then you have a, kind of magnetic field, like a toroidal magnetic field, right? The magnetic field, that toroidal part, it has to be optically thick, based on the luminosity that we calculate. So that means we have to be looking into or close into the magnetic pole in order for us to see this emission. Okay. And that's what we thought. And then, all right, so that could be the, emission from like a, kind of close to surface, and that emits the lower energy, and it's always there, even if it rotates, there has to be some sort of, visible emission from that kind of near surface polar region area. Yep. And then on top of it, this high energy component that we see could be coming from some sort of low altitude. It's not at the surface, but low altitude, low enough of altitude that we can still see from time to time, but it's like a hot spot, like a hot little belt area that we may see, from time to time, but other time it's obscured by the toroidal field area. So that we thought was the feasible explanation, for more natural kind of explanation for this higher energy component appearing, from time to time, and then at the end in the segment 2, it's a very periodic behavior, right? And there could be other interpretation also, like magnetic reconnection or something like that happens at the much higher altitude also, but this seems to be the low altitude, hot spot seems to be more natural explanation for this, we thought. So that's what we're reporting as a.
Sorry, do we know if this
Sure.
is a single or binary or something like that?
This is isolated, I think.
Isolated.
It has, I think so.
Okay.
It's not in binary.
Okay. Thank you. Mm-hmm.
So yes, that's our interpretation for this, especially for this segment 2 peaks, that high energy component appears in periodic behavior.
Very nice. Very nice.
Thank you.
Well, let's see, let's just make sure. Yeah. Okay. Yuki, thank you so much for walking us through your very lovely APQ letter. And you hinted at it a couple of times. So let me ask, where do we go from here? Let's say over the next 5 years, are there additional Fermi data to analyze? Will there be new, nicer observations coming online? Are there already discoveries of other similar systems? Not that I want you to spill your next research project, but where do we kind of go, let's say, over the next 5 years on improving our knowledge of these kind of systems?
Sure. Actually, this burst is not resting yet. It's still active. Okay. And it became active earlier this year. And then the last one, I think in early or mid-July, we saw bursts from this source. So, it's still going on, and, we're kind of hoping, for a giant flare or something like that, something is building up, it seems like. So we're waiting, and we keep monitoring these sources. Cool. Yes, hopefully, I don't know. Cool. So yes, we have, whenever we see bursts, we're doing untriggered event search from these bursts. And we have a lot of SGRs also, other SGRs that are active. So we're, continuously monitoring all these active SGRs, which is kind of getting a lot of attention these days because of the FRB connection. Right. Well, yes. Yes. And one thing that our team reported, the galactic, yes. One thing that our team reported earlier was that these short gamma ray events, the short bursts, property of these bursts, we only have one event, but the coinciding, FRB X-ray burst, that is apparently really hard. Okay. It was observed by Chinese satellite, and it was reported. So based on that, their analysis, that is really high energy, like E peak is 80 keV or something like that. So that is very different from the rest of the bursts. Yeah. Although it looks like a regular burst, from the light curve point of view. So, something like that, we're waiting for, something like that to happen. And so that we have more samples. Yes, exactly. That coincides with the FRB or something that, contributes to understanding of FRBs. That would be fantastic if that happens.
That would be awesome. That would be great. Well, I look forward to some of your future articles that are analyzing these.
All right.
So very cool. So Yuki, I want to thank you once again for walking us through that lovely APJ letter. Very nice.
Thank you very much. Thank you for having me.
Thank you. And that'll do, everyone. And I hope this made your astronomy day just a little bit better, and we'll see you on the next one. Thank you. Bye-bye.
Bye.